Okay, so let's do another application of Gauss law. Let's just assume that we have some conductor. This is conductor. On the surface, we have some charge density. Let's say positively charged. And sigma is the surface charge density, that is the charge per unit length. Now, what is the electric field? Well, your friend had a guess, sigma over 2 epsilon 0. It's a wrong guess. It's not correct. It's not sigma over 2 epsilon 0. Why? Okay, sigma over epsilon 0 is the right answer, but why? Now, what is the electric field here? This is my conductor. Infinite. What is the electric field over there? It's a conductor. No, hold on. The electric field inside the conductor, infinite. No. So what is the electric field in this conductor? The surface is infinite. It's an infinitely large conductor filling half of the universe. This surface is flat. What is the electric field inside the conductor? Come on, we just said it in the beginning of the last lecture. What is the electric field inside the conductor? It's 0. Of course, electric field out of the conductor, here it won't be 0. But what can you say about, let's say, the magnitude, the direction, etc.? It is pointing upward. Why? Okay, why not in this direction or in that direction? Okay, so it can start perpendicular and then curve. Why not? Okay, because of the magic word symmetry. So, I mean, if you just imagine a mirror just going like this, the system doesn't change, so the electric field shouldn't change. So the electric field lines are always perpendicular. It's in the upward direction. It already tells you that the magnitude of the electric field is constant because the electric field line, their density doesn't change. So the electric field in the upper half, let's say this is our z-axis, it is E0 in the z direction. This is our electric field. Now, what kind of a Gauss surface can we take? A cylinder. Well, we don't even need to bother about the cross-sectional shape. I mean, we can just take such a shape. I would rather have it vertical. That's the only constraint I have. This is the Gauss surface that I will imagine. The main criteria is that the sides should be vertical. And the top and the bottom should be horizontal. So that the sides, I will have no contribution to the Gauss integral since the electric field is vertical. And from the top and the bottom, I don't need to worry about the angles that the top surface or the bottom surface makes. Now we can talk about the Gauss integral. What will be I can divide this integral into various parts. I have the top part, I have the bottom, I have the sides. Now, on the sides, the surface elements are in which direction? On the sides. There. I mean, just imagine this is my Gauss surface. Cut it from here. This is our cylinder. So on the sides, the the electric fields are pointing in this direction. No, not the electric field, the area vector will be perpendicular to the surface. Well, you can choose it to point in this direction or in the other direction, in the inside, it doesn't matter. But just for simplicity, let's just assume that it's pointing outside. In the top, it will be pointing up. In the bottom, it will be pointing downward. So on the sides, I know that the electric field should be in the vertical direction. But if the area element is in this direction, they are perpendicular to each other. There's no contribution to this integral from the sides. From the bottom, well, in the bottom, the electric field is 0. The bottom is inside my conductor, so there's no contribution from the bottom. The only contribution will be from the top. Now, on the top, ds is pointing upward. Electric field is pointing upward. So they are in the same direction. So the scalar product of two vectors pointing in the same direction is just the product of the two, the magnitudes. The magnitude is E0. Well, E0 is just a constant. Let's say this is E0. Let's just name the top area by A. This is E0 times A. This is the Gauss integral. E0, we don't know. That's what we are trying to extract. Now we can use Gauss Law. And Gauss Law tells me that this should be equal to sigma A over epsilon 0. Because sigma A is the total charge inside my Gauss surface. Now I have charges over here, but they are not inside my Gauss surface. The only charge in my Gauss surface is over here. And they are they are distributed over an area A, and sigma is nothing but the charge per unit area. So if you multiply charge per unit area by the area, we get the total charge. A's we can just cancel, so E0 is equal to sigma over epsilon 0. So it's not 2 epsilon 0, it's just epsilon 0. When we had this infinite plane of charge, uniform charge distribution, the electric field was E over 2 epsilon 0 on both sides. Now the difference between this case and the other case is that if you have just a very thin planar charge distribution, the electric field lines, they just can, they spread in two directions. But in this case, since we have a conductor over here, the electric field lines cannot go into the conductor. So they have to go to the other side, out of the conductor. All of them should go to the others out. So that's why we don't have this factor 2 in the denominator. Any questions? Y is this one. This one. The upper one. Okay, so you see, this is what we understand, what you should understand by this integral over here, this integral sign, is that you have this surface. You are talking about a surface integral. You take the surface, divide it into very small areas all around. And for each one of those very small areas, you should define this ds pointing from inside to outside. And you should calculate the electric field vector at the point of your area, take the scalar product of those two vectors, and sum over the contributions of each one of these very small bits. This is the meaning of this sign, symbols over here. Now, some of these areas, they are on the sides. So I have a very small area over here. The ds vector corresponding to this area is in this direction, perpendicular to that area, pointing from inside to outside. But my electric field is in this direction. They are perpendicular to each other, E and ds. E and ds are perpendicular to each other for this very small area element over here, for one of them. But it is perpendicular to all the ds's for these very small elements on the sides of my cylinder. It basically means that to this sum, there is no contribution from the S's on the sides of my cylinder. So there's no contribution from the side. Well, there's no contribution from the bottom because for every ds at the bottom, the electric field is 0 because the bottom is inside my conductor. So there's no contribution from here. I only get contribution to this sum from the ds elements on the top part. And when I divide all this surface into very small segments, some of them are here. They will contribute to my integral. This one will not, neither the one over here. So that is why I use the symbol. Here I write top just to denote that I am only considering area elements on the top of the cylinder, not the sides, not the bottom. And then the next is at the top, the magnitude is E0. The S is in the same direction as the Z vector. So this is nothing but E times ds, E0 times ds. And E0 is just a constant, so we just take it out. Other questions? Now let's do another example. Now we always said that, okay, if you have a metal, if you put it inside in an electric field, the charges in the metal will move around. There will be some other charge distribution created in the metal such that the electric field will be perpendicular to the surface all everywhere. Now the question is, what is the charge density on the surface of the metal? So suppose that we have this point charge over here plus Q. We can imagine some conductor. Well, there will be some negative charges over here, some positive charges over here. I mean, we will not be calculating it explicitly, but suppose we know the electric field. We can easily measure the electric field everywhere. If we measure the electric field everywhere, if E is known, what is sigma, let's say, at the point R? Sigma is the surface charge density. How can we determine that? No. Now, up to now, we have always been dealing with cases when we are given the charge, how we can determine the electric field. Now, this is just reversing it around. Given the electric field, how can you determine the charge? So somehow we measure the electric field. What can we say about the charge? In this case, the charge on the surface of the metal. Okay, the first guess is wrong. Come on, you have two choices. The other one? Yes. Okay, that's the correct answer. You integrate, but how? And why? Now, up to now, we have been dealing with cases where, okay, given the electric field, given the charge distribution, we discussed how do we calculate the electric field. Now, in this question, somebody tells you that, hey, look, in this region of space, this is the electric field we have. How can you determine the charge distribution in that region of space? So somebody just comes and tells you, okay, look, here, this is the electric field. So what is the charge density, charge distribution here on the surface of the metal? How can we determine that one? Oh, yes. If? Okay, we know the electric field everywhere. How? Which law? Okay, so the electric field is 1/4 pi epsilon 0 q over r squared r. Wrong. Electric field is not equal to that one. Don't forget the conditions under which given statements are valid. This is valid only for a point charge. We have already seen many cases where this law of the electric field is not true. We had the dipole, for example, in which case the electric field, the magnitude went as 1 over r cubed. We had an infinite charge distribution. The electric field decreased as 1 over r. We had an infinite plane charge distribution where we had the electric field just constant. It didn't change with r. So don't say that, okay, the electric field is 1 over 4 pi epsilon 0 q over r squared. That is wrong. That is the electric field of a point charge only. So what do we know about the conductors? Okay, we will use the Gauss law somehow. Okay, so knowns. We know Gauss law. Well, it is nice because Gauss law relates the electric field to the charge. Given the electric field, if we integrate it, we find the charge. Once we find the charge, we can find the charge density. Dividing by the charge over volume or the charge over the surface area will give us the charge density. So, okay, that is why we will be using Gauss law. Now, how can we make use of the Gauss law? What do we know about this system? Your friend has said no electric field inside the conductor. What else do we know? We have to somehow use all these known facts to relate the electric field to the charge by using the Gauss law. But there is one more ingredient that we will be using. Symmetry, I don't see any symmetry over here. What is the direction of the electric field? On the surface. Anywhere, here or here, since we are talking about the conductor, E is perpendicular to the surface. So these are the known things. Now, in practice, in fact, these would be enough to determine the charge over everywhere. Well, the simplest thing we will do is just, okay, go to the surface. We know the electric field over here. Choose any Gauss surface. Apply the Gauss law. That will give you the total charge inside that surface, and we are done. Well, we would rather have a simpler expression, though. So this is the shape we have. This is the system that we are studying. Now let's look at this part, and let me enlarge it. It looks something like this. Let me take this part, and let me enlarge it even further. It is like this. Here we have the conductor. Now, this looks quite similar, no? It is the same problem as this one. On the surface, the electric field line should be perpendicular. And since I'm very, very close to the surface, I mean, they should start perpendicular to the surface. And since I'm very, very close to the surface, they didn't yet have time to diverge, to change their direction. So within what we see over here, the electric field lines are perpendicular to the surface. They are parallel to each other. The electric field is constant in this region. It's not constant everywhere, but in this region, it is constant. and perpendicular to the surface. Almost. Now let's take a Gauss surface. Let's just, just as in the previous case, we can imagine a Gauss surface in the shape of a cylinder. The integral of E dot ds on this cylinder, let's just assume that this is A. This is equal to minus E times A. Just due to the very same reasons in the previous example. The electric field is perpendicular to the surface. This area is parallel to the surface. From the sides, I don't receive any contribution because on the sides, the S is perpendicular to the electric field. In this region, the electric field is 0 because we are inside the conductor. On the top of the cylinder, E and ds, they are just pointing in opposite directions. ds is pointing outward, electric field is pointing inward. So that's why I have this minus sign over there. And this should be equal to the charge density at this region, sigma r times the A over epsilon 0. A's cancel, so sigma r is equal to minus E over epsilon 0. And we are done. This is the surface charge density at this point. This is the electric field at that point. E times epsilon 0. This is just for a region, you are right. But this region can be any region. Let me write it properly over here. Sigma will be equal to epsilon 0 times E dot n. N is this vector on the surface, a unit vector. Now you want to find the electric field at this region. Fine, go to that point. Calculate the electric field at that point. Calculate n at that point. Calculate this scalar product, multiply with epsilon 0, that gives you sigma. At that point. Well, it's just a means of showing this minus sign. You see here, the electric field is perpendicular. E is the magnitude of the perpendicular electric field. So if you calculate E dot n, E dot n is E magnitude times magnitude of n times cosine of the angle between the two. So E is the magnitude, minus 1. In this case, n is pointing outward, electric field is pointing inwards. So cosine of theta is 180. Cosine of 180 is this minus 1. It's just a fancy way of writing that minus 1. If the electric field is going into the surface, it's just telling me that there's negative charges over there. If it is leaving the surface, it is just telling me that there are positive charges over there. Now this way of writing it down, this way of writing it down just takes into account both cases. But if the since the vector n is pointing outward, If this is a positive, if electric field is going out, this is telling me that sigma is positive. If the electric field is going into the surface, this is telling me that the electric field is, this charge density is negative. Yes. We know the electric field. Of course, this is the electric field on the surface, by the way, not the electric field over here. This is only the electric field on the surface. This is the charge density on the surface. Now this equation doesn't have any meaning away from the surface. Just take any point on the surface. E is the electric field on that point, and is the unit vector pointing out of that surface. And then this is the charge density. You get the total charge. Other questions? For example, if it's a neutral conductor, then you will get 0. Sure. Depends on your surface. You have to sum over all the surface. Don't worry, you will get a homework from that. Other questions? Well, there will be some effects when if you start the conductors moving around. But that, just wait a bit. Now there was also another question in your pre-reports. I mean, in some cases we will be dealing with moving charges even in electrostatics. For example, in your friend's question, what happens if you move the conductor? We can still treat it in electrostatics, because in that case, still the charges that create the electric field are at rest. That is what we basically mean statics. The charges that creates the electric field, and we will now see potential, not now, but on Thursday, the charges that create those things, they are at rest. It's the unit vector pointing from inside the conductor to the out of the conductor and perpendicular to the surface everywhere. So n vector changes from point to point. So this is our conductor. N vector here is in this direction, n vector here is in this direction, etc. You see, vectors exist even if you don't choose some coordinate axis. You can talk about the vectors without choosing a coordinate axis. But if you want to talk about the components of vectors, then you have to choose some coordinate axis. So that's why in this problem I didn't specify any coordinate axis. I don't really need one. If I want to write down, let's say this r vector, if I want to write an explicit representation of it, then I have to choose some coordinate axis. Other questions? Somebody new. Get ready. And I will not start the electric potential today. So this is a neutral conductor. Inside, I place a positive Q charge. Here there is a negative Q charge. Here there is a positive Q charge. Here there is a minus 3Q charge. And then I imagine this surface. This is our Gauss surface. Let's say this is surface 1. You don't need to write this question down. This is my surface 2. And you need to calculate, okay, this is the direction of the S. This is the direction of the S for the other surface. Now A for S1, B for S2. And after the quiz, you can leave. You don't need to draw this question.